Yes. Yes, sir, we can hear you.
Oh, okay, fine, thank you. So, sorry for this marathon session. Yeah, so I am Professor Venkatesh Babu. I am the convener of this video analytics lab. Okay, so this lab is about 11 years old, 11 to 12 years old now, right? So I will just take you through what we are doing in the lab and why we are doing this kind of a research work. Okay, so look at this. What do we do? So we are solving various computer vision problems using ML techniques, especially deep learning technique. So we extensively use deep learning for various applications of computer vision. Okay. So I will let you know what is computer vision. This may be a new term itself for you. Some of you may not have heard about this. Okay. Also, the lab's objective is to kind of a video analytics lab means the video feeds are coming from the camera, and basically we wanted to feed these video feeds to a machine and then ask the machine to understand what is happening. Because why this problem is important is because physical security is always very important, and we are having growing number of CCTV cameras everywhere in the city, right? And for example, if you want to monitor a city like Bangalore, you need huge amounts of cameras, maybe runs into 1,000, 10,000 cameras, right? And all these camera feeds are coming to a kind of a centralized server, and where you wanted to look at these feeds and then say whether things are normal. These are not possible by employing people who can see these screens and then assess things, because this is simply not scalable, because the huge number of cameras you need to deploy so many people, right? And it's not going to be a reliable solution, right? So that's why the number of cameras are quite less, like a kind of a shop or a small campus. Then you have hundreds of cameras, and probably some people are deployed to watch these things. At a city scale, it is impossible to do thing. So that's where this video analytics comes into picture. So for example, if you look at this, there is a video analytics module which actually replaces the human brain, right? So, so this module is going to replace the human brain. Also, the amount of data that you think, thousands of cameras pump huge amount of data, and you need huge computational power to process these video feeds and then detect whether things are fine or not. Okay, so that gives you a kind of what is intelligent surveillance system actually do, right? But realizing this particular intelligence is the bigger problem for us, and that is what comes under image understanding or computer vision or whatever you call, okay, visual analytics, right? So why this vision is a difficult problem? Okay, for example, we see things, we keep seeing, you're seeing this lecture, and when you go out, you see things, and you have the assessment of the situation, whether things are fine or something is wrong, there is some accident, all those things. But these are all actually very quickly processed by your brain, right? Knowingly or unknowingly, you are not conscious about that, right? But it takes up about 70% of your brain neurons to process your visual signal. Okay, so out of six, four, five senses, visual sense is the one which takes up huge amount of computational power, uh, computational power of your brain. So that shows how difficult the problem of vision is. Okay. So for example, auditory, all the other things use the rest of 30% of your neurons. Okay. So why it is a difficult problem? For example, if you see an image here, you can always say there is a nice apple, green apple, fresh apple, all those things. Without putting effort, you can say this thing. But whereas if I show the right hand side, you will say, I wonder what is this? You're showing some matrix with numbers. Okay. What to do with this kind of thing. So, but this is what the machine sees actually, right? Only the numbers and matrices. Now, actually, the image is actually represented in terms of these numbers, right? There are three matrices, one for R, G, and B. So you have three such matrices, and then that is what is rendered as an image for your uh, perception. So now our challenge is actually these numbers are available and how to go from here to this left, right hand side to the left hand side. Okay. And this is the gap that we are talking about. So you have to build some algorithm which consumes this matrix and the numbers and then try to say something meaningful at the other end. Okay. So this is all about computer vision or image understanding. So given an image in the matrix form like this, can you write some code, some algorithm on top of this, which takes this as an input and then says a meaningful output, a semantic. This is what we call this a semantic. So you're moving from a syntactic input to a semantic output. Okay. So the problem is huge here because we don't know what kind of algorithm that you have to put on top of this to get actually the semantic meaning, right? Okay. And this is for a simple object like this. If you have some complex scene like this, then the problem gets much more difficult. Okay. So yeah, these are all kind of examples for the more difficult cases because we still don't know what kind of a features that we should extract to fine grained classification that we can do using this kind of features. Okay. So those kind of features are still absent. Similarly, depth is one thing that we always perceive whenever we look at an image, right? When you take a photograph, you had no issues in understanding what is the object that is closer to you, what is far away from this, right? But it is a huge problem for computer vision because nobody is going to tell this object is closer to the camera, that object is far away from the camera, right? So that is another major issue that we face in computer vision. Okay, so this is one example where we perceive one object is bigger than the other object, whereas actually the both objects are of same size. The computer will say, oh, both objects are of same size, whereas we understand one is bigger than the other. Okay, so of course we are correct because the background is given, right? It's a tunnel kind of a thing. And the bigger object is in the background and the closer one is actually the smaller object. In a real situation, you can see all the cars, the computer says all the cars are same, whereas we say the first car is smaller than the last one, right? So this kind of understanding comes from the context, basically looking at the surrounding, how the car is placed, and which is closer to the camera, which is far away from the camera. All this decoding is happening in your brain, and then you can say clearly what is the small, what is big. Okay. This is another major challenge that we face in computer vision. Similarly, some complex objects like this. So here, if you look at this particular image is having a lot of noise, even then we could, if we keep seeing, you will find out some object is here. This looks like animal, all those things. Even you can say the various parts of the object as you keep looking. Okay. So whereas vision algorithms will miserably fail here. Okay. So now you know so vision is actually the one which takes up a lot of your neurons of your brain, and then you try to infer using those neurons, right? Okay. I will skip some of this thing. So this is one nice example where all of you fail to recognize what object it is, right? Whereas if I show the context, probably some of you can get the object easily, right? So for example, you will see the context gives you the rail tracks here, and then you will immediately say there is going to be a train. Okay. So object alone is not useful. You need even the context to understand the picture. Okay. So this is the full image. And what are the challenges that we face when we develop computer vision algorithms? Okay. So these are the challenges that mainly we have to address. So illumination change because lighting condition keeps on changing for the, based on where you are located. Also occlusion, right? So you will never ever see full object all the time, right? Some object is blocking the other object. So that is what we call occlusion. And scale. The same object looks bigger when it is closer to the camera and looks smaller when it is away from the camera. Similarly, the objects need not be a rigid object. It can move around here and there. And then each time the deformation is another major issue. And background clutter is another thing. It's very hard to detect even the objects when the clutter is there. Similarly, intra-class variations, you can look at all these, though they belong to chair class, you will see each one is having a different design, colors, right? And various attributes. All are meant for sitting. Still, putting all these things in the same class is a much more challenging task. Okay. So this is about the introduction to vision. So now if you look at what we were doing some before 2012, that is before deep, and what we do after deep. Okay. So yeah, I have another 10 minutes. I can go through this. So all these things started with the AlexNet paper that came in 2012, where they used trained a model using 1.3 million images across 1,000 classes, and then showed a huge dip in the error rate. So you can see before deep models, yeah, the error rate was somewhere around 26% or so. Suddenly this model came and reduced more than around 10%, and then showed, yeah, the deep model is much, much better than the classical ones. From that time onwards, you can see all the other models that were reducing the error, all were deep models. Okay. So as the time progressed, we are going from a deep to much, much deeper model with more multiple layers. Okay. So in conventional recognition approach, even before deep, how we were doing were, so we just used the images and extracted some kind of intelligent features and use these features for training the classifier, because we cannot train a major classifier using huge dimensional inputs. So basically the extracted features actually takes the gist of the image and then represent in the lesser dimensional space. So that is what is used for training the classifier. But we always had so many issues with this. There are so many features, so many machine learning algorithms. We don't know what to use, which one goes well with other one, right? And this bottleneck, that is the feature extraction on ML, this bottleneck was one which preventing your performance, right? So in deep models, we are actually going to merge these two models together and ask the machine itself to extract the features, the best features for the particular task, right? So this is mostly a kind of inspired from the brain when we see the image, how we understand things, because through the visual pathway, you extract some simpler features, and as you go deeper in V1, V2, and V4, you start extracting some complex features before understanding the image. The similar principle is followed even in the deep models, where you initially extract the simpler features, right, pixel level and edges, and after that, on the last layer, you extract some features that are kind of meaningful object kind of features. Okay. It's not only in vision, even across other modalities, speech as well as NLP, we do the same. Yeah, so basically, yeah, in deep what we are doing, so we just feed the raw data as the input and then ask the machine to kind of extract the suitable features to get the final task. So yeah, basically, yeah. So this is kind of a end-to-end network where you are actually backpropagating from the inference end to the input end. Okay, so this is where the classification that happens. So error gets generated at this end, and the error is backpropagated to modify the network weights. And even if you look at these features, you can see the initial layers will have some kind of a primitive features like oriented edges, And as you go deeper, you can see there is some kind of complex features are extracted by the filters. And yeah, here you can see these filters actually respond. These neurons respond to the very complex objects as well. And what is the effect of this deep learning on vision? So this is the paper that we have discussed, which started this deep model for various vision applications. And after that, we had so many things like object detection, face recognition, segmentation, captioning. Right. So this is the first paper, 2012 paper, which we saw. And this is the paper from Facebook where they had millions of faces, all your faces are with Facebook. So they trained a huge model and then it can give one of the best recognition accuracy. It was surpassing even the human recognition. And object detection was done in 2014 RCNN. Then there were more different variants of RCNN, fast RCNN, faster RCNN, YOLO, so many things came out. But this is the initial work which actually kickstarted the research. Also, you can see it also kickstarted the autonomous driving kind of a scenario. So once you know how you can reliably detect the objects in front of you, so why don't you keep a camera in front of the car and then can detect all the objects and maybe you can do autonomous driving there. So this particular direction actually kickstarted even the autonomous driving applications. And segmentation is just a very hard problem. And yeah, deep models performed the classical ones, even in this. And other interesting application came out as image captioning. Given an image, can you describe the image? All these captions that are given here are generated by image captioning model. Okay. So man in black shirt is playing guitar, all those things. It's very realistic, right? Okay. So this is dense caption for each window of the image. It is giving you a description. For example, if you look at the dark blue window, so bus has a number. The bus has a number. Oh, that is the one. Yeah. And you get, oh, maybe this one that is. So if you look at this bigger window, yeah, this is a city scene, street scene. Okay. And if you look at this gray window, it says actually, where is it? A green traffic light. Yeah, it says. So it makes basically each interesting region, it actually gives you a kind of a description. So there are many fascinating things that happen actually, even optical flow, all those things. So yeah, most of the industry, if you look at, so whenever people say I'm a deep expert, basically once that model is trained, you can use this as a black box actually. So give the data, get the output, and even without much knowledge, you can fine tune some of the parameters very easily and then get better performance. So that's why there's huge number of people participate in this kind of a deep learning research, right? Because all it requires is kind of a basic coding skills. As long as you have that, you can do wonders. And yeah, you have a lot of large scale vision data sets generated because these are all data driven approaches. Without data, data is the fuel for these models. So you have a better data, huge amount of data, then you can always come up with the best model using this data, right? So actually the model is kind of the, what is it? Quality of the model very much depends upon the quality of the data that you have actually. So in our lab, for example, if you want to look at what we were doing actually, so this is some of the works that happened in 2015-16, where we wanted to find out, develop a model which actually predicts the location where we are looking at the image. This is called as the saliency prediction. Okay, so where we tend to look at the image, because for example, if you look at this image, yeah, so basically the sign is the one which is catchy. So everyone tend to look at that location. So we trained a model which actually predicts very accurately the salient locations of the image. So you can see these are the outputs that is. So ground truth is collected through eye tracker device. And deepfakes is our proposed approach, which actually comes much closer to this ground truth. So the same work actually extended for segmenting as well. So you can not only predict the eye fixations, also you can do the segmentation of the meaningful objects. Also, we were doing some kind of a counting. For example, wherever you have crowd scenario, you want to count the number of objects in this uh, images, right? So this is called object counting across various domains. Yeah, we were all some interested in counting how many people were attending this particular gathering, right? So it's a very difficult task. It's manually very laborious. So machine learning is a very good substitute where it can predict, if it can predict very accurately the number of people in the crowd, yeah, that will be very useful for crowd management. Okay. Oh yeah. We proposed a series of models where we were showing better performance using various deep architectures. So this is one of the highly cited work published in 2017, which we call as switching CNN for crowd counting, done by Deepak, was a PhD student here. Yeah, the work was further extended and you used some very nice architectures to improve the performance. Okay, so this was in CPR 18. Also, one of the my PhD students worked on sketch recognition. Basically, sketches are one very nice uh, kind of image where hardly you have information, right? Only 5% of the pixels are occupied, remaining are white, okay, white or black. So even with this minimalistic thing, whether we can do classification or segmentation, all these things. So this was his thesis, where he was exploring various aspects of sketch recognition and analysis. Also, we proposed uh, GAN, which can generate the sketches with a limited amount of data. Yeah. So this was called Delhi GAN and published in CPR 17. And sketch parsing is another very interesting work because we wanted to segment the bus, various parts of the bus, the sketch. So we want to have the windshield separately, wheels, body, all those things separately. So how to segment this sketch? So this was a huge architecture which was proposed for the segmentation. And you can see, so this animal, the head, the body, and the legs, they were all nicely segmented. Yeah. Even for this vehicles, you can see the wheels, body, seat, all those things are nicely segmented for animals as well. Yeah. So yeah, one more interesting work done by the PhD student, Ram, is HDR image. All your mobile phones will have this HDR functionality where you have to take dark as well as the bright contrasting environment. You want to have a pleasant picture here, right? So you have darker and how to compose all these four images and then get a nice HDR image here. Okay, so this was the work done by Ram here. And for this, the deep fuse, which is the first CNN architecture proposed for fusing multi-exposure images for creating the HDR image. The problem here is you don't have the ground truth, so you have to use this unsupervised way of training this model. Okay, so we used a SSIM based loss function for training the model here. So maybe since we are running out of time, I'll cover one. So another important topic that uh, the research is going on in the lab is about adversarial images, how to attack the deep model. For example, if you look at this image, left-hand image, there is a dog, and right-hand image, there is a slightly perturbed version of the dog. You can't even perceive the perturbation. With this perturbation, the dog is, the class is changed to paintbrush. Okay, so which means you can always add the targeted noise. These are the crafted noise to your image and then make your model fail very easily. almost for 90% of the images, it gives you wrong classes. So that shows the deep models are quite fragile to the adversarial attacks. And yeah, this won't happen with the human brain, which is quite powerful. So that shows the huge gap between the stability of the human brain and the fragility, vulnerability of a deep model. And yeah, in this direction also we had a couple of works where we wanted to generate the UAPs, universal adversarial perturbations, that can attack the models, right? So yeah, these are some of the results that were obtained. So we were working in towards how to make our deep model robust, how to protect my model from the adversarial attack. So there are multiple works along this direction because so adversarial training is one major important step in getting the robust model. And this model takes a huge amount of training time, about 10x more than the normal training. So here our objective is to how can we train very close to the normal training complexity and get the adversarially robust model. Okay, so these are the couple of works in this direction which are published in the recent CVPR. This is our adversarial team that worked in this. Also, this is another CVPR work where given a single image, whether we can predict the depth, okay, which human brain easily does, when we train a model which can get the depth from a single model. So 3D object reconstruction is another area of interest. Even one single image can predict the 3D model of this particular object, which is again a very, very challenging one. One single image, it's very hard to get a 3D model out of this. So we trained a model network, which actually can give you a 3D model of the given single image input. Yeah, so since we're running out of time, so we are at 6 o'clock. I'll stop here and if you have any questions, right, you can mail me or you can ask any of the lab members. Okay, so I just want to just create interest in whatever we are doing. Hope I have done my job. Hope you are all interested in doing some of the cutting edge research in computer vision using deep learning, right? Thank you. So maybe where's my the lab? So this is where not even CDS is there. VAL dot CDS. Yes. So this is our